Welcome back, Science 9 students. Today we are going to learn about energy and its forms. In this opening slide, there's actually a lot going on here in terms of energy, so let's kind of discuss this a little bit. Obviously this is an avalanche happening, you can see that from the picture, but let's talk about before the avalanche is happening. So let's just say we take all this snow and put it up here at the top again. And let's just say it's just sitting there before the avalanche happens. You might say that that snow has like the potential to fall, and you would be right. That this snow, when it's up here, is actually the technical vocab word for it is stored potential energy. That's one of the energy forms we're going to talk about today. So when it's up here not moving, it's got potential to move though, so we call that potential energy. Then let's just say some sort of sound wave or something gets this thing to go and it breaks free and it starts to fall down here. When it is falling, the potential energy is getting converted into a different form of energy, which we call kinetic energy. Which is moving energy. So when it goes from here, it was stored, avalanche is happening, now it's being converted into kinetic energy. So those are the two forms we're going to talk about today, potential and kinetic energy. Really nice opening slide. All right, hold on, I gotta fix this iPad. So it says, how are energy and work related? Well, energy is basically the ability to do work. We learned about work in chapter 14. You guys know that work is force times distance. So energy is the ability to do work. Work is essentially a transfer of energy. Okay, so they are definitely closely related. They actually use the same units. So when we measure, potential energy or kinetic energy, we use the joule. If we measure work, force times distance, we also use the joule. So they're definitely closely related. So let's talk about the first kind of energy that we're learning today, which is kinetic energy. This is basically the energy of motion. When an object is in motion, it has energy. So if I take this ball and I raise it up to here, now it has the potential to do work, especially if I go like this. Boom, if I drop it. All right, so now we have potential energy up here. I drop the ball. When the ball gets dropped, that's kinetic energy. That's motion energy. So the kinetic energy of an object depends on its mass and speed. So if I take another ball, let's see, just give me 1 second, I gotta find that lacrosse ball. Oh yeah. So if I have two, this one's probably half the mass as this lacrosse ball. If I drop both of these, one of them is going to have more kinetic energy, and it's actually going to be the lacrosse ball. And it's because it has more mass. You guys know that gravity is constant, so that when you drop them, they fall at the same, acceleration, same rate of change for speed. So doubling the mass in the formula doubles the kinetic energy. Or if you double the speed, it's going to quadruple the kinetic energy. I'll show you guys that with a couple examples here. The formula is pretty simple. To calculate kinetic energy, take 1/2 times the mass times the velocity squared. All right, or speed squared. So let's think of the tennis ball and the lacrosse ball here. Because let's just say we double the mass, and like we're learning here, doubling the mass doubles the kinetic energy. Let's prove it. All right, so I'm just gonna go TB for tennis ball, LB for lacrosse ball, and let's just say they're falling at the same speed. Just for simplicity, I'll just call it a speed of 10. Let's just go 1/2, and let's say tennis ball has a mass of, let's just keep it simple, 1, because that's an easy number to work with, times 10 squared. Let's double the lacrosse ball, let's say 2. So over here, we'll say 1/2 times 2 times 10 squared. So if you do the math, this would be 1/2 times 100. So the tennis ball would have 50 joules of kinetic energy. Let's look at the lacrosse ball. 1/2 of 2 is 1, times 100 would be 100. So there is the proof right there. So if you double the mass of an object, it's going to double the kinetic energy. Like we can see with the tennis ball and the lacrosse ball. You double the mass, you have double the kinetic energy. But if you could double the speed, that's going to quadruple it. I'm going to show you doubling the speed in a different example. So let's move on from this. The units of kinetic energy would be joules, like you saw in that example. And let's add one more thing here. Since we're talking about units, mass is going to be in kilograms. Velocity is going to be in meters per second. So if you're given an object in grams, convert it to a kilogram. If it's kilometers per hour, we want to convert it to meters per second. But as long as we have these two units, we can just plug in the numbers and we'll get the correct answer. All right, so here's what we're going to do. The next 2 slides is going to show the result of, let's skip this one. If we double the speed of a bird, it's going to show kind of what happens here. So what I'm going to do is we'll solve this problem, and then we'll solve this problem. Then the only thing that you'll notice difference is we doubled the speed of the bird. So it went from 8 to 16. And like it said there in that big key point, that if we double the speed, then the kinetic energy should be quadrupled. Well, let's see if that's right. All right, so let's look at this problem right here. So we have a 0.1 kilogram bird is flying at a constant speed of 8 meters per second. What is the bird's kinetic energy? So kinetic energy equals 1/2 mv squared. Pretty easy formula to work with. Just make sure your units are good. Kilogram, yep. So I can plug that number in for mass, 0.10. Meters per second, we're good. So then 8 squared. So I get kinetic energy of 3.2, and then our unit would be joule for kinetic energy. So remember that, 3.2, because now we're going to solve this problem where we doubled the speed. And actually, let me go like this. I'm just going to do a reminder here, 32 joules, okay? That was for the bird going half the speed. So now let's solve this problem here. We got kinetic energy equals 1/2 mv squared. 1/2. The mass is still 0.1. Velocity is 16 squared. Hey, Mr. Forsberg wants to say hi.
Morning.
He's playing with the lights over there like a little kid.
Just like real crap class for you.
Yeah, just like a real class. He can be the distracting student here.
You throw this food at you.
He throws his food at you, he says. So good old Mr. Forsberg. Here's another science teacher at Crosby. Let's see here. So I'm getting 16 squared times 0.1 times 0.5. I'm getting an answer of 12.8. Which is making me question the other problem. So let's go back. So that one's 12.8. This one Oop, hold on. Oh, I see what we did. Hold on. I see the, or do I? Nope. All right. Let's see. The 32 is probably not right. Let's go back to this problem. So we got kinetic energy equals 1/2 mv squared. Let's see where we went wrong. 1/2 times 0.1 times 8 squared. So we got squared times 0.1 times 0.5. Ah, there it is. 3.2. Oh, maybe I transferred it wrong. Yeah, so 3.2, I suppose that's what I did. I wrote it down wrong. So put a decimal there with the third 3.2. It's not 32, it's 3.2. And then on this slide, this should be 3.2 joules. I'm wondering, hey, it's not adding up. That's definitely not quadrupled. But we solved this one, and we ended up getting 12.8. So now the question is, if we double the speed of the bird, do we quadruple the kinetic energy? And the answer would be yes. If you take 12.8 and divide it by 4, I get 3.2. Or if I take 3.2 and I multiply it times 4, I get 12.8. So doubling the speed of an object quadruples the kinetic energy. So let's go back to these two big key points. I proved to you that doubling the mass doubles the kinetic energy. You saw that with the tennis ball and lacrosse ball. Doubling the speed quadruples the kinetic energy. You guys saw that with the bird. It went from 3.2 joules of energy to 12.8 joules of energy. That was quadrupled. All right, so that's basically kinetic energy. I'll leave some of these problems for you, except for, let's look at this one. So that's a little bit different. So we have a 50 kilogram cheetah has a kinetic energy of 18,000 joules. How fast is the cheetah running? So we have the kinetic energy equals 1/2 mv squared. So with this problem, it's different because we're given the 18,000 joules. So plug that in for your kinetic energy, and then 1/2 times the mass, which is 50 times v squared. All right, now we have it set up. We'll do our algebra. 25 v squared divided by 25 cancels. So we're looking at 720. Now you might go, oh, 720 is the answer. Very nice. Take the square root. Second, square root, 720. And then we get our answer. Velocity equals 26. Let's see your point. Let's just round to the nearest 10, 26.8. And because it's speed, we'll go meters per second. So there it is. We got some class clowns in the back there. They're trying to make me laugh, but it's kind of working. All right, so now let's talk about potential energy. Potential energy is basically the energy that is stored as a result of a change in the position or the shape. So we mentioned the ball example. If I raise the ball up, now I have more stored potential energy. So I can drop it and it's available to do work. We looked at that avalanche example at the beginning of the hour, that all that snow was up at the top of the mountain. It had the potential to do work. I like to bow hunt, so that's a classic example of potential energy. When the bow is at rest, it doesn't have the potential to do work. But when I pull the bow back, put work into the system, now it has the potential to do work, because when I release the bow, the arrow is going to go. All right, so let's talk about potential energy. Even musicians, when they are pulling on these strings, it has the potential to do work, so that energy is getting transferred into the sound energy. So there's actually going to be two types of potential energy that we're going to learn about. One type is going to be the gravitational potential energy, and the other type we're going to learn about is elastic potential energy. There's formulas for both. We're just going to look at the gravitational potential energy. So gravitational potential energy is this. it's where the energy is going to depend upon that object's height. So if I take this, raise it up at X amount of height, that's what it's going to depend on. The higher the ball goes up, the more potential energy it has. So if I pick it up to here, it doesn't have a lot of potential energy. If I pick it up here, it has more, and so on and so on. Let's see here. So a diver has a lot of great potential energy. A diver's going to climb up the ladder. That's where it's gaining that energy. So it's actually taking kinetic energy. So like when I raise this up, I'm using kinetic energy to gain potential energy. Same thing with a diver. So to calculate it, it's pretty simple. It's just PE, potential energy, equals mgh. So mass is going to be in kilograms. So that's important. So if you're given a problem where it's in grams, make sure you convert it. So mass is in kilograms. G, you guys should recall, that's gravity. That's going to be 9.8 meters per second squared. And the height's going to be in meters because of the fact that we're using 9.8 meters per second squared for our acceleration. So if we're given a height in kilometers or centimeters, we'd want to convert that to a meter. So that's pretty simple. That's how we calculate potential energy. Now height is kind of important. It's like, well, what's the height in reference to? So I could say that, oh, hey, this ball goes from here to there, the countertop. That would be the height in terms of potential energy. But I could take the same ball and drop it behind the counter. So here has a lot more potential energy than right here. So it just depends on whatever the reference level is going to be, whether it's the ground, cabinet. But when you do your problems, you would specify where the ground level was. Okay, so let's just look at a couple problems. Potential energy, super easy to calculate. It says, what is the potential energy relative to the water surface of a diver at 10 meters of a 10 meter high diving platform? Suppose she has a mass of 50 kilograms. So we'll do the old stick figure. Boom, boom, boom. So we have a height of 10 meters. And this person has a mass of 50 kilometers. All right, so potential energy equals mgh. So the mass is 50 times gravity, 9.8, times the height, 10 meters. Okay, so pretty simple. 50 times 9.8 times 10, we get 4,900 joules. All right, so let's skip ahead here. Let's see here. They're all pretty much the same. It's just mass times gravity times height. I'm gonna leave those for you guys. The last thing we're gonna talk about is elastic potential energy. So this is the potential of an object that can be stretched or compressed. So obviously the bow and arrow would classify as elastic potential energy. And there's different formulas for this. It's actually 1/2 kx squared. We're not going to use that for this class, but there is another formula for it. The shocks on a bike would be elastic potential energy. And then I think what we'll do is we'll leave it there because we'll talk about forms of energy in a different video.